Hi, and welcome back. What about classification? We discussed that the output of a regression is a number, but for classification, things are different. Since the outputs are categories, like cats and dogs, we need a better suited strategy. The most common loss function used for classification is cross-entropy, and it is defined as L of y and t equals minus the sum of the targets times the natural log of the outputs. Time for an example before I lose your interest. Let's consider our cats and dogs problem. This time, we will have a third category, horse. Here's an image labeled as dog. The label is the target. But how does it look in numerical terms? Well, the target vector t for this photo would be 0, 1, 0. The first 0 means it is not a cat, the 1 shows it is a dog, and the third 0 indicates it is not a horse. Okay, let's examine a different image. This time, it will be labeled horse. Its target vector is 0, 0, 1. Imagine the outputs of our model for these two images are 0.4, 0.4, 0.2 for the first image, and 0.1, 0.2, 0.7 for the second. After some machine learning transformations, these vectors show the probabilities for each photo to be a cat, a dog, or a horse. We will learn how to create these vectors later in the course. For now, we just need to know how to interpret them. The first vector shows that, according to our algorithm, there is a 0.4 or a 40% chance that the first photo is a cat, 40% it is a dog, and 20% it is a horse. So that's the interpretation of these vectors. What about the cross-entropy of each photo? The cross-entropy loss for the first image is minus 0 times natural log of 0.4, minus 1 times natural log of 0.4, minus 0 times natural log of 0.2. This equals approximately 0.92. The cross-entropy loss for the second image is minus 0 times natural log of 0.1, minus 0 times the natural log of 0.2, minus 1 times the natural log of 0.7, which equals approximately 0.36. As we already know, the lower the loss function, or the cross-entropy in this case, the more accurate the model. So, what's the meaning of these two cross-entropies? They show the second loss is lower, therefore, its prediction is superior. This is what we expected. For the first image, the model was not sure if the photo was of a dog or a cat. There was an equal 40% probability for both options. We can oppose this to the second photo, where the model was 70% sure it was a horse. Thus, the cross-entropy was lower. Okay. An important note is that, with classification, our target vectors consist of a bunch of zeros and a 1, which indicates the correct category. Therefore, we could simplify the above formulas too. Minus the log of the probability of the output for the correct answer. Here's an illustration of how our initial formulas would change. Alright, those were examples of commonly used loss functions for regression and classification. Most regression and classification problems are solved by using them. But there are other loss functions that can help us resolve a problem. We must emphasize that any function that holds the basic property of being higher for worse results and lower for better results can be a loss function. We will often use this observation when coding. It will all become clear when we see them in action. That's all for now. Thanks for watching.